Hey there, team! Chemistry Coach coming at you. Video number 7 in our chemical compounds series. Let's get away from the naming and all that stuff and get to the math. Yes! So logical! Let's do some percent composition. And sometimes when I teach this, I switch around the formulas. Sometimes I just introduce basic formulas and then we do the math first. Sometimes I'll show you how to name things and then we'll do the math. Depends how I feel at the time, but it really doesn't matter what order we go in, right? I can just give you the formula and we can do all this stuff. So what's important with this? A lot of times, and I ran into this in graduate school when I was working on my PhD, I worked on something called XPS, X-ray photoelectron spectrometry, or spectroscopy actually. It's been a long time, a really long time. Yeah, I'm not going to go through the details of it, but I was able to use this machine to determine kind of what elements were on the surface of a substance, usually some kind of solid or metal. And I could get the percent of each one. I could say, hey, this is, 15.2% oxygen, 22.8% sulfur, 38% carbon, whatever it is. It doesn't matter. I could break things down. It didn't tell me what it was, but commonly people would come by and say, hey, I made this new substance. Could you tell me the percent composition by mass of what it is? And I can say, okay, like I said, 22% mass this, blah, 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 blah. And then they would go on their merry way and try to figure out what it was. But they needed that data, that percent composition, to help them figure out what this unknown species was. Very common in the real world as well. Bomb analysis, poisons, think detective, your CSA type stuff. You got the crime scenes. And somebody comes in and wants to know, hey, what poison did somebody use to kill this? Or what type of bomb did they use to blow up this building or something? And they could take, trace residues of chemical compounds, bring it to a laboratory, run it through some experiments, which, if you move on and become a chemistry major, maybe you'll actually run these particular experiments. And we can get a percent breakdown by mass of all the different elements in that unknown substance. Boop! That's what this is. That's what percent composition is. So say there's 3 elements. The total should add up to 100%. So it's this percent this one, that percent that one, that percent that one. That's what a percent composition is. And almost always that'll be by mass. I guess you could do other units, but I've always seen it as percent by mass breakdown. And given that, and I'll show you in the next video how to take that percent mass data given from a laboratory and calculate or get to the true molecular formula for that particular species. All right. So in general, and a percent, again, is just a parts per hundred. It's a ratio. It's a part over whole. You can think of it as a part over whole, the whole being the sample, the part being the element of interest. And we can think of it as a parts per hundred, which we will use in our calculations in a little bit. So the mass percent of, let's say, subspecies X, element X, whatever it is. So say we have, sodium carbonate. We want to know the percent by mass of carbon. So X would be carbon in that case. We would take the mass of carbon in grams divided by the mass of the whole substance. 2 different types of calculations we're going to look at. What if we're given laboratory data and we're actually given those masses? It's pretty easy to calculate. But what if we're not given data? What if we're just given a chemical formula? It's not an unknown anymore, right? So either we're given this data and we can calculate an unknown, their identity, or if we're given identity, we can get the percent composition by mass of any specific element in that, or the entire species, every single element. That'd be the percent composition breakdown. We don't even have to do just elements. We can do any portion of the substance. So say you have a hydrate or something, and you've got some compound, and it's hydrated, so it's got some water bound to it. Well, we can figure out the mass percent of water in that particular substance. So it doesn't have to be a specific element, any portion of that substance. So let's do the 2 types of calculations and have at it. Once you see how they're done, piece of cake, gang. Here are the 2 and only 2 types of problems you're going to run into. So expect one or the other, or possibly both on the quiz or an exam. Most commonly what we do in a laboratory is we have some known substance or an unknown substance, one of the 2, right? Doesn't really matter whether we know the formula or not. And then we gather, maybe we weigh the sample, and then either decompose it to break it down and collect one of the elements and weigh that. And then we have the mass of the element and the mass of the sample. Maybe it's a hydrate. We weigh the whole hydrate, heat it up, drive the water off. And from that, we can figure out the mass of water released and calculate the percent mass of water. Hold on, you're going to do one of those labs for my class. So it doesn't matter whether you know the formula or not. We're actually experimentally doing something to it to break it down into its components and measure the masses of those. Pretty easy to calculate. We'll do an example of that. And theoretically, let's say we have no data, right? This would be something you do in lab because the point of lab is to do something. But let's say we only have the chemical formula, right? We know the mole ratios of the different elements in the species, and we want to know the percent by mass of one of those elements or some portion of that particular substance. I'll show you how to calculate the percent by mass of that portion of the substance without any data whatsoever, as long as you know the chemical formula, because we can get some really interesting information just from the chemical formula. So let's start with the first one, very similar to things you're going to be doing in laboratory using that equation I gave you earlier. Get your calculators out and your brains ready. For the first type of problem where we're in a laboratory situation or maybe a homework problem or an exam where we're given laboratory experimental data, right? Here's what our approach is. Or if you're designing a laboratory, even in that case. So let's say we have an unknown substance or a known substance, and we want to get the mass percent of some element in that substance or some portion of that substance, like I said, water or something. Well, measure the sample mass. That's the easy part. Or if it's a solid, whatever it is, weigh it out, you're good to go. Hey, I got it. Whether you use a top loader balance to 2 decimal places, milligram balance to 3 decimal places, or an analytical balance to 4 decimal places, depends how many significant digits you want in your answer. So once you got the mass of the whole thing, remember, make sure you weigh that before you decompose it or react it with something else, because you won't be able to get that back, right? Then measure directly or calculate indirectly based on other measurements the mass of the element that you're trying to figure the mass percent of, or the portion of that particular substance you're trying to figure the mass percent of, unless you're doing all the elements, right? The total percent composition breakdown. And last but not least, use that equation we gave you where you take the mass of that particular portion or element divided by the mass of the whole sample. That gives you the part over whole ratio, and then times it by 100. You're good to go. It's so easy once you know what you're doing. Let's do an example problem. I'll write it up on the board. Once I write the problem down, pause it and see if you can calculate it before I do. Hopefully this is fairly straightforward for you. If not, do a bunch of problems and get used to it. And we're going to do a lab fairly similar to this. This is going to be a little more simple. I'm going to make you think more in lab. Here we go. We've got an unknown sample. No idea what it is, but we know it's a hydrate. So it's got some water bound to it. So if we heat that up, that water's going to go bye-bye, right? So we should know intuitively the mass will go down after we heat it, correct? We heat it up, dry the water off, the mass is going to drop. So let's weigh that sample before we heat it. So we get 1.428 grams. Looks like we did that on a milligram balance. Good to 3 decimal places, right? We heat it up and then drive all the water off. However experimentally that is done. We're going to be doing that in several steps in lab. Heat it, weigh it, heat it again, make sure we heat it until that mass stays constant and we're sure all that water is gone. And let's say after we're all said and done, heat it up, let it cool down. You don't want to weigh things that are really hot, right? So let it cool down close to room temperature. And it weighs 1.247 grams after we're done. And that dropped. Makes sense, right? We drove off. Now the difference is the mass of the water that was driven off, correct? Correct. So what is the percent mass of water? So do those steps. Get the mass of the sample, which was given to you directly. That one you don't need to calculate. We always measure that one. Get the mass of the portion or element of interest, and either that was weighed directly or you have to calculate it indirectly. And that mass that we weigh directly is the mass of the dried hydrate. It's no longer a hydrate. It's the anhydrous compound. We want the mass of water, so we're going to have to go through the back door and calculate that. And then just divide the mass of the water by the mass of the sample. Right? Should be pretty straightforward. So let's see what we got here. Let's get the mass of the water first. Would you agree that'll be the mass of the sample minus the grams of the sample after heating? So let's do before heating minus the grams of the sample after heating, or however you want to label those, right? So we've got 1.428 grams minus 1.247 grams. If you got that backwards, you'd get a negative mass. That would not make any sense at all, right? What's a negative mass mean? It went into a black hole. I created a black hole. I don't even know what that means. 3 decimals, 3 decimals. We're limited to 3 decimal places. So I get 0.181 grams of water. Right? The difference before and after. So we know the mass of the water, which is the portion of interest we're after. So now we can calculate the percent mass. So we'll put our equation, and again, that's a part over whole. The part's the water. So that'd be grams of water. We could have done just oxygen or hydrogen or something if we had more data, but we're interested in just the water. Over the grams of the sample. And we take that ratio times 100. That 100 is exact, so we're limited by the significant digits of our masses. And again, that's the sample originally. That's the hydrated sample, not the dehydrated sample. So the grams of the water, 0.181 grams, over the grams of the sample originally, 1.428 grams. And then let's multiply that by 100 to get it into a percentage, right? So part over whole. So it looks like we got 3 significant digits in our mass of water, because that leading 0 doesn't count, right? And we got 4 significant digits in our original sample mass, and that 100 is exact. So we're good to 3 significant digits. So pop that out. I get 12.675. Good to 3 significant digits. 12.675%. That's closer to 12.7 than 12.6, right? So the 12.7% water by mass. Right? Maybe we have a list. We can look up a table of different types of hydrated species with known percent by masses of water. We can kind of narrow that down to a couple species. We might have to do more experiments to really get the true identity. Not too bad. You'll be doing something very similar to this in lab. Now let's do a problem where we don't have any data. We're not given any experimental data, just the formula of the actual compound. We can calculate the percent by mass of any portion of that lickety-split, gang. Let me show you how to do that. This is one of my absolute favorite problems in chemistry, believe it or not. Once you know how to set it up, now you may have been taught a different way to do this. That's fine, but in my class, I want you to set it up in a way that makes a lot of sense to the reader. I'm always about, does your work make sense to somebody who's reading it? Whether it's me or another student or your mom or your sister or your boyfriend or girlfriend, I don't care. Does it make sense? If you just puke an answer out there, they're going, how did you get that answer? Right? And on my exam, if it's wrong, I can't give you partial credit. But if you set it up right and I can see how your brain's working, I can go, that's where you have -2 instead of -12 or something. So what if we're given only a chemical formula? And remember, the chemical formula provides you the mole-to-mole ratios of the different components of that particular species. Right? So what we're going to do, and because this is all we're given, is set up the mole ratio. We're going to assume exactly 1 mole of that particular substance or species. That's the whole, right? We're going to put that in the denominator. And then we're going to look at the chemical formula and go, well, how many moles of that element are in that substance? For example, if I had sodium sulfide, Na2S. Well, 1 mole of sodium sulfide would have 2 moles of sodium and 1 mole of sulfur. Oh, so I can put 1 mole of sulfur over 2 moles of sodium. 1 mole of sulfur over 1 mole of sodium sulfide. Stop the pain. Or I could go 2 moles of sodium over 1 mole of the whole thing, sodium sulfide. So you always just assume 1 mole of the whole thing, stick it in the bottom, and put however many moles from the chemical formula of that portion of it on the top in the numerator. That's the mole ratio, part over whole. Right? We don't have gram data, so we can't do it in grams. We do it in moles. Then we use a unit line equation, take the moles of the element, use the atomic mass to convert to moles, take the 1 mole of the substance on the bottom, use the molar mass to convert to grams. And so now we have the gram ratio. You'll end up with grams of the element over grams of the substance using a unit line equation. It's pretty slick. Very easy to follow, too. It only takes you a couple minutes to do it. When you know how to do it, boom! Do enough of them, just take a couple minutes on the exam. Thanks for the easy points, Locks. And then we just take that mass ratio times 100. We're good to go. All right, let's show you how to set that up. I think just one example, you'll be like, I think I got it. All right, I was a boogerhead on this one. I didn't even give you the chemical formula. I just gave you the name. You should be able to go names to formulas, right? We went through that. Should be able to go from a chemical formula to a name and a name to a chemical formula. So we've got lead 2-phosphate, and that's all we know. There's no data. What's the mass percent of lead in it, right? So this would be a purely theoretical calculation. Then we could go do this in lab and see if we get a value that matches it. So we can't do anything without the chemical formula. So we've got lead 2, right? Type 2 metal. I love those ones. Phosphate, if you haven't memorized the polyatomic ions, you're toast. That's PO4. 3 minus. Those are not equal and opposite, so they do not go in a 1-to-1 ratio, correct? So the least common multiple between 2 and 3 is 6. So 2 times 3 gives me 6, so I need 3 of the lead 2 ions, and 3 times 2 gives me negative 6. I need 2 of the phosphates, so positive 6 plus negative 6 gives me 0. If you're struggling with that, go back to the prior videos. So that's going to be 3 leads for every 2 phosphates. There we go. Now we can set this up. Here we go, gang. Let's do the percent mass of lead. And all we have is the mole ratio. So let's assume 1 mole of the whole thing. Let's put that on the bottom. So let's put 1 mole of lead 2-phosphate in the denominator. And 1 mole of that contains 2 moles of phosphate and 3 moles of lead. Or you could say 2 moles of phosphorus and 8 moles of oxygen. So I could have done oxygen or phosphorus or lead or phosphate. Right? I could have done any of these, but I'm doing the lead. So that'll be 3 moles. If I could spell lead right. Boom, that 3 comes down there. There you go. That's the first step. Just once you got that, this is a piece of cake, gang. Now let's just get the atomic mass of lead to convert it to grams. Get the molar mass of lead 2-phosphate, convert that to grams, times it by 100. Wada bing, wada boom. Go ahead and do that for me real quick. All right. So I'm going to erase this real quick so I got some space for getting this baby up here. Boom. There we go. So I'm going to find lead. Oh, where's my periodic table? Never leave home without it. So I've got lead. Where the heck is lead? It's over here somewhere. I got a 207.2 for lead. And you know, whatever the periodic table you have there. So I'm going to go, and moles is in the numerator of lead, right? So for 1 mole of lead, I keep spelling PB wrong. How do you spell an element symbol wrong? I just did it twice. So there's 207.2 grams of lead per mole of lead, right on? So moles of lead cancels out. Ultimately, what I'm going to end up with is the mass of the element, or the portion I'm interested in, X, over the mass of the substance, which takes us back to the original chemical formula. Ah, baby. All right. Now let's assume 1 mole of the whole substance. So we've got 1 mole. Oh, I spelled it right this time. Take that. Oh, this is going to be a fun molar mass, isn't it? Oop, I need some space here to multiply it by 100, don't I? We're going to have to multiply that by 100. Do I have black marker on my nose? Ooh! This is going to be highly unpleasant. So, you know lead's 207.2, so multiply that by 3, and that'll limit you to 1 decimal place. Let's look up phosphorus. I think that has 18 trillion decimal places or something. I cannot read that without my glasses, I don't think. Whatever that's 30.973761? Is that what phosphorus says? I need my glasses. That's so many decimal places. It's not going to matter, though, because lead's going to limit us. So multiply phosphorus times 2. And oxygen's 15.9994. Can't get away from that one. So take 15.9994 times 8, right? 2 times 4 is 8. And then the phosphorus times 2. And the lead times 3, limited to 1 decimal place because of the lead. All right, what do you get? I get 811.5. Put the vertical dash line there because we're stuck to 1 decimal place because of the lead. 811.5 0.42 grams of the lead 2-phosphate. That allows you to cancel out moles. See the beautiful unit line equation? Very easy for someone to read and see what's going on there. Now let's track our significant digits. This is an exact number, right? That 3, that's from a chemical formula. That's exact. The lead atomic mass has 4 significant digits. And the lead 2-phosphate also has 4 significant digits. That 100 is exact. So I'm limited to 4 significant digits. A lot of times in these calculations, you'll get a truckload, 5, 6, 7 significant digits based on whatever atomic masses you use from the periodic table. Because the first step is exact, and then the 100 is exact. So you're limited by the atomic mass and the molar mass. Same setup every single time, gang, people, whoever you are. Take the formula. Assume 1 mole of whole species. How many moles of what you're interested in go on top? Use the atomic mass, molar mass, times 100, done. It's the same thing every time. And when you train yourself that way and you get to the exam, there is a chemical formula. Let's assume 1 mole of the whole thing on the bottom. How many moles of the thing of interest go on top? Use the atomic mass to convert that to grams. Use the molar mass to convert that to grams. Multiply by 100. Track the significant digits. I am done. That's how you function on a test. Just puke it all out and you're good to go. All right, to 4 significant digits. I was just doing all that so you had time to calculate this, right? So you got it done. I guess 76.59. Oh, I'm starting to sweat. It's getting hot in here. 76.5949% lead. Good to 4 significant digits. We're going to round that. That's close to halfway, but not quite. It's less than 5. So it's closer to 76.59 than 76.60. So that's going to go 76.59% lead in lead 2-phosphate. So it looks like a huge majority of lead 2-phosphate, even though there's only 3 atoms of lead compared to like 8 of oxygen. Just lead's so massive, it dominates the mass percent from that. And I can do the same thing for oxygen. I would just put 8 moles of oxygen here and put 15.999994 there, right? Or I could do the phosphorus, go 2 moles of phosphorus and then put the atomic mass of phosphorus. I could do it for all 3 and get the percent composition. Not too bad, guys. You can do it. This will be it. You're going to really look forward to these calculations, these types of problems on exams. Go, thank you, Lux. I've got this one.